July 6, 1988, Piper Alpha Oil Platform, North Sea, 9:50 p.m. The evening shift is settling into routine on Piper Alpha, a massive oil and gas production platform standing on steel legs 120 miles northeast of Aberdeen, Scotland. The platform rises from the cold North Sea waters like a small industrial city, its decks stacked with equipment, pipes, vessels and machinery. Flames burn continuously from the flare tower, consuming excess gas in a controlled burn that illuminates the platform against the darkening summer sky. The low rumble of pumps, compressors and generators creates a constant background noise that workers learn to tune out. In the control room, operators monitor gauges, screens and readouts tracking the complex systems that extract crude oil and natural gas from wells thousands of feet below the seabed, separate the oil from gas and water, and pump it through pipelines to shore. The night shift has taken over from the day crew, handover notes have been reviewed. Systems appear normal, everything seems routine on what should be an ordinary summer evening in the North Sea, but something is fundamentally wrong on Piper Alpha, and nobody in the control room knows it yet. A safety valve, a critical component designed to prevent dangerous pressure buildup, has been removed from a condensate pump for routine maintenance. The pump is not supposed to be used. A blind flange has been installed to seal the opening where the valve was removed, but it is only hand-tightened, not properly secured. And crucially, the night shift operators have not been properly informed that this pump is out of service. The failure of communication between day and night shifts, the inadequate documentation of maintenance work, and the decision to operate systems without proper verification of their status are about to combine in a catastrophic sequence. Within 20 minutes, Piper Alpha will experience a massive gas explosion. Within 2 hours, the platform will be an inferno of burning oil and gas, and by morning, 167 men will be dead in what will become the world's worst offshore oil disaster. This is the story of Piper Alpha, how a missing safety valve that nobody checked, a permit-to-work system that failed, and a corporate culture that prioritized production over safety combined to destroy a platform and kill 167 workers in an inferno so intense it could be seen from the Scottish mainland 120 miles away. Piper Alpha was not an old or decrepit platform. It had been installed in the North Sea in 1976, designed and built by one of the world's leading offshore engineering firms. The platform was a production facility designed to extract oil and gas from subsea wells, process it on the platform, and send it to shore through pipelines. At the time of its installation, Piper Alpha represented state-of-the-art offshore technology. The platform was operated by Occidental Petroleum, an American oil company that had acquired significant North Sea assets. Occidental had taken over operation of Piper Alpha in 1974 before the platform was even completed. The company invested heavily in North Sea production, recognizing that the oil and gas reserves beneath the cold waters between Scotland and Norway represented enormous potential value. By the late 1980s, Piper Alpha had been producing for over a decade. The platform had been modified and upgraded multiple times as production requirements changed and as additional wells were tied into its processing systems. Originally designed primarily for oil production, the platform had been adapted to handle increasing amounts of natural gas. These modifications meant that Piper Alpha's systems were complex, with multiple pipelines, processing trains and interconnected equipment. The platform itself was a massive structure. It stood on steel jacket legs anchored to the seabed in approximately 474 feet of water. The main platform decks rose about 175 feet above sea level, with the flare tower extending even higher. The accommodation module, where workers lived during their 2-week rotation offshore, was a separate structure connected to the main platform. At any given time, approximately 226 workers were on Piper Alpha, a combination of Occidental employees and contractors performing various production, maintenance and support functions. Life on an offshore platform like Piper Alpha followed a regimented routine. Workers flew by helicopter from Aberdeen to the platform, where they worked 12-hour shifts for 14 consecutive days before flying back to shore for 14 days off. The work was demanding, long hours in an industrial environment, isolated from families, subject to North Sea weather that could be brutal even in summer. But the pay was good by UK standards, and many workers built careers in the North Sea oil industry, moving between platforms and companies as opportunities arose. The work itself was dangerous even under the best circumstances. Oil and gas production involves handling highly flammable and explosive materials under high pressure. Hydrogen sulfide, a toxic gas that can be present in oil and gas wells, can kill in minutes at high concentrations. The machinery is heavy and powerful, capable of crushing or severing limbs if safety procedures are not followed. The North Sea environment adds additional hazards: cold water that can kill from hypothermia in minutes, waves that can sweep workers off decks, weather that can prevent helicopter evacuation for days. Safety procedures and systems were supposed to manage these risks. Occidental, like all North Sea operators, was required to maintain extensive safety management systems covering everything from equipment maintenance to emergency response. The UK government's Department of Energy regulated offshore oil and gas operations, conducting inspections and reviewing safety cases. Industry associations developed recommended practices that operators were expected to follow. But safety systems are only as effective as their implementation. Procedures written in manuals must be followed in practice. Equipment must be properly maintained. Workers must be adequately trained. Management must genuinely prioritize safety over production when conflicts arise. And crucially, the culture of an organization, the unwritten assumptions and priorities that guide behavior when nobody is watching, must support safe operations rather than undermining them. On Piper Alpha, there were warning signs that safety culture was problematic. Workers had raised concerns about maintenance backlogs, about procedures not being followed, about production pressure overriding safety considerations. Union representatives had flagged issues to management. Government inspectors had noted deficiencies in some areas. But these warnings had not led to fundamental changes in how the platform was operated. One particular issue that would prove catastrophic was the permit to work system. This system was designed to control maintenance and modification work on the platform. When equipment needed to be taken out of service for maintenance, a permit would be issued specifying what work was being done, what safety precautions were required, and what the status of the equipment was. When work was completed, the permit would be closed out, and the equipment could be returned to service. Between shifts, information about ongoing work and equipment status was supposed to be communicated so that incoming operators knew what systems were available. In theory, this system should prevent exactly the kind of accident that was about to occur: someone trying to operate equipment that was not ready for service. In practice, the permit to work system on Piper Alpha had weaknesses. Permits were sometimes not properly filled out. Communication between shifts was sometimes inadequate. And the pressure to maintain production meant that there was reluctance to take equipment out of service or to delay operations while verifying system status. July 6, 1988, began as a routine day on Piper Alpha. The day shift came on duty at 6 a.m. and began their normal routines. Production continued from the oil and gas wells connected to the platform. Maintenance work proceeded on various systems. The weather was decent by North Sea standards, overcast but not stormy, with moderate seas and reasonable visibility. During the day shift, a maintenance crew began work on one of the condensate injection pumps. Condensate is a liquid hydrocarbon that condenses from natural gas under certain conditions. Piper Alpha had two condensate injection pumps, designated Pump A and Pump B, which were used to pump condensate back into the oil stream for export through the pipeline to shore. The pumps operated at high pressure over 1,800 pounds per square inch to inject the condensate into the pressurized oil pipeline. Each pump had a pressure safety valve, a critical safety device that would automatically open if pressure exceeded safe limits, releasing fluid to prevent the pump or piping from rupturing. These pressure safety valves were essential safety equipment required by regulations and by basic engineering principles. Operating a high-pressure pump without a functioning pressure safety valve would be extremely dangerous, as any pressure surge or blockage could cause catastrophic failure. On this particular day, Pump A's pressure safety valve was due for routine recertification, a periodic test and inspection required to ensure the valve would function properly if needed. The maintenance crew began the work by isolating Pump A from the system, depressurizing the pump, and then removing the pressure safety valve for testing. This was standard maintenance work, performed regularly on offshore platforms. The maintenance crew removed the valve and found that it could not be recertified that day. Either the testing equipment was not available or the valve would need to be sent on shore for testing at a workshop. Rather than reinstalling the valve and waiting for another opportunity to test it, the crew installed a blind flange, a metal plate that seals the opening where the valve had been connected. The blind flange was hand-tightened with nuts on the mounting bolts, but crucially it was not fully tightened to the torque specifications required for a pressure seal. This would later prove to be a fatal error. A permit to work was issued for this maintenance work. The permit should have clearly indicated that pump A was out of service, that the pressure safety valve had been removed, and that the pump should not be operated. The permit should have been signed and logged in a way that would make this status clear to anyone who might need to know, including the night shift operators who would take over later that evening. But the permit to work system failed in multiple ways. The permit itself may not have been clearly written or may have been ambiguous about the equipment status. The permit may not have been properly communicated to the control room operators who would need to know about it. Or the permit information may have been recorded in logs that were not checked by the incoming night shift. Whatever the specific failure, the result was that when the night shift took over at 6 p.m., they were not aware that pump A was out of service and should not be used. The day shift maintenance crew finished their work on pump A, or rather they stopped work for the day without completing it. The blind flange was installed but not properly tightened. The pressure safety valve was removed and presumably taken to a workshop. No clear "Do Not Operate" tag was attached to pump A. No physical lockout device prevented someone from starting the pump. The pump appeared ready for service to anyone who did not know about the ongoing maintenance work. At 6 p.m., the night shift took over. The shift handover process involved the incoming shift supervisor meeting with the outgoing supervisor to review the platform status, ongoing work, and any issues that needed attention. But the handover was apparently incomplete or inadequate. The night shift supervisor was not clearly informed about pump A's status, or if he was informed, the information was not properly communicated to the control room operators who would actually be operating the equipment. The night shift settled into routine. Production continued. Operators monitored their systems. Everything seemed normal, but a dangerous condition existed that nobody in the control room knew about. Pump A was not ready for service, lacking its pressure safety valve, and having only a hand-tightened blind flange to seal the high-pressure opening. At approximately 9:50 p.m., something occurred that required condensate pumping capacity. Possibly there was an upset in the process that increased condensate production. Possibly the operating pump B was showing signs of problems. Possibly an operator simply decided that running both pumps would be more efficient. Whatever the reason, an operator in the control room decided to start pump A. The operator had no reason to think this was dangerous. From his perspective, he was simply starting a pump that appeared to be available. There was no clear indication in the control room that pump A was out of service. The pump controls worked normally. When the operator pressed the start button, pump A started up. The electric motor began turning, the pump began operating, and pressure began to build in the pump and its connected piping. But pump A had no pressure safety valve. The blind flange that sealed the opening where the valve should have been was only hand-tightened, not capable of withstanding the full operating pressure of over 1,800 psi. As pressure built up in the pump, it pushed against the blind flange. The hand-tightened nuts could not hold against this pressure. The blind flange began to leak. High-pressure condensate, a mixture of liquid hydrocarbons, began spraying from around the edges of the improperly sealed blind flange. The leak started small but grew rapidly as pressure increased, and as the force of the escaping fluid worked the nuts looser. Within seconds, condensate was spraying forcefully from the failed seal, forming a high-pressure jet of flammable liquid that vaporized into a cloud of explosive gas as it hit the atmosphere. Condensate is similar to gasoline, highly flammable, easily vaporized, producing explosive vapor clouds when released into air. The leak was occurring in a confined space, the module that housed the condensate pumps, surrounded by walls and equipment that would trap and concentrate the vapor cloud. Alarms may have sounded in the control room as pressure sensors detected the problem. Operators may have realized something was wrong and tried to shut down pump A. But events were moving too fast. The vapor cloud from the leaking condensate found an ignition source. On an offshore platform filled with electrical equipment, hot surfaces, and industrial machinery, ignition sources are everywhere. A spark from electrical equipment, a hot surface on a pump or pipe, a static discharge, any of these could have ignited the vapor cloud. At approximately 9:58 p.m., about 8 minutes after Pump A had been started, the vapor cloud ignited. The initial explosion was devastating. The condensate vapor cloud, mixed with air in the confined space of the pump module, detonated with tremendous force. The explosion was not a simple fire but a detonation, a supersonic combustion wave that propagated through the vapor cloud faster than the speed of sound, generating a powerful blast wave that destroyed everything in its path. The pump module was blown apart, metal walls were torn open or blown out, equipment was shattered, pipes were severed, personnel in or near the module at the time of the explosion were killed instantly by the blast wave and the fireball that followed. The explosion's force transmitted through the platform's structure, shaking the entire installation. Workers throughout Piper Alpha felt the violent shock, heard the deafening blast, and saw or felt the platform lurch. In the accommodation module, off-duty workers were jolted from beds or knocked off their feet. Many had been sleeping, reading, watching television, or socializing in common areas when the explosion occurred. The sudden violent shock was unlike anything most had experienced offshore. Some initially thought a supply vessel had collided with the platform. Others thought there had been a major equipment failure or dropped load. Few immediately recognized the explosion for what it was, a catastrophic release and ignition of flammable gas that signaled the beginning of a disaster. In the control room, operators faced a sudden cascade of alarms as sensors throughout the platform detected the explosion, pressure drops in multiple systems, loss of equipment and fire. The alarm system, designed to alert operators to problems, became overwhelmed by the sheer number of simultaneous alarms, screens filled with red warning indicators. Audio alarms created a cacophony of competing sounds. Operators trained to respond systematically to alarms found themselves facing a situation their training had not prepared them for, not a single equipment failure or process upset, but a catastrophic event that had damaged multiple systems simultaneously. The operator's immediate instinct was to try to understand what had happened and to begin emergency shutdown procedures, but their ability to assess the situation was severely limited. The explosion had damaged or destroyed sensors in the affected area, meaning they had no instrumentation telling them what was happening in the pump module. Visual inspection was impossible. The module was filled with smoke and flame, and operators in the control room could not see into it. Radio communication with workers in the affected area was not possible, either because those workers were dead or injured, or because communication systems had been damaged. What the operators could see from their instruments was alarming but incomplete. Pressure had dropped in the condensate system, indicating a major leak. Flow measurements showed that large quantities of material were escaping. Temperature sensors near the pump module showed rapid increases, indicating fire. But the operators did not know the scale of the damage, did not know how many people had been killed or injured, and did not know whether the fires could be controlled or would spread. The initial explosion, catastrophic as it was only the beginning of the disaster. The blast had ruptured multiple pipes and vessels containing flammable materials under pressure. Oil, gas and condensate were now leaking from damaged systems throughout the affected area and igniting, creating intense fires in multiple locations. The explosion had also compromised fire protection systems, severing water pipes that supplied deluge systems, damaging fire pumps and their control systems, and destroying equipment that was supposed to contain and suppress fires. Within minutes of the initial explosion, major fires were burning in the pump module area and spreading to adjacent sections of the platform. The fires were fed by continuous leaks of oil and gas from ruptured pipes and damaged equipment. On an offshore platform, everything is interconnected through a complex network of pipes carrying flammable materials at high pressure. Once fires start and pipes begin failing from heat exposure, the situation can escalate rapidly as each failure feeds more fuel to the fires and exposes more systems to heat and flame. The heat from the initial fires began affecting nearby piping and equipment. Steel pipes carrying oil and gas at high pressure were exposed to flames. As the steel heated, it lost strength and became more vulnerable to failure. Process equipment, vessels, heat exchangers, separators also heated up, and the materials inside them expanded and pressurized. Some of this equipment was designed to withstand fire for a limited time, but the intensity of the hydrocarbon fires on Piper Alpha exceeded design assumptions. Within minutes, additional pipes and vessels were failing, releasing more fuel into the fires and causing secondary explosions. The platform's fire protection systems, sophisticated as they were, proved inadequate to the disaster unfolding. Piper Alpha had water deluge systems, networks of pipes with spray nozzles that could release enormous quantities of seawater onto fires when activated. These systems were designed to cool equipment, suppress flames, and prevent fire spread. But the deluge systems required massive amounts of water at high pressure, which had to be supplied by firewater pumps. The firewater pumps on Piper Alpha were diesel-driven and located on the platform. This design had seemed reasonable when the platform was built. Diesel engines could run independently of electrical power, providing firewater even if the main power generation systems failed. But the placement of the pumps and their control systems proved to be a fatal vulnerability. The pumps were not adequately protected from the effects of explosions and fires that they were supposed to help control. When the initial explosion occurred, the firewater pumps should have started automatically as pressure dropped in the firewater system. Some accounts suggest that at least one pump did start, but the pumps and their associated equipment were quickly affected by the fires and subsequent explosions. The diesel engines that drove the pumps drew combustion air from the surrounding atmosphere, which was now contaminated with smoke, gas vapors, and potentially explosive mixtures. The fuel tanks and lines supplying diesel to the engines were exposed to heat from the fires. Control systems for the pumps were damaged by blast effects or fire. Within a short time after the initial explosion, the firewater system on Piper Alpha had lost capacity. The deluge systems that should have been pouring thousands of gallons per minute of seawater onto the fires were either not operating or providing inadequate flow and pressure. Without effective fire suppression, the fires grew in intensity and spread unchecked through the affected areas of the platform. The platform's emergency response procedures called for a systematic response to major incidents. The offshore installation manager, the senior Occidental representative on the platform, and the person ultimately responsible for all operations was supposed to take command and coordinate the emergency response. A dedicated emergency control center was supposed to be activated, where key personnel could gather to assess the situation, coordinate firefighting efforts, and make decisions about evacuation if necessary. But the violence and speed of the disaster overwhelmed these carefully planned procedures. The initial explosion had occurred without warning, giving no time for preparation or pre-positioning of response resources. The explosion had killed or seriously injured some personnel who had designated emergency response roles. The fires spread faster than responders could mobilize. Communication systems that emergency coordinators depended on were damaged or overwhelmed by the number of people trying to use them simultaneously. The offshore installation manager, whose identity would later be confirmed among the dead, was attempting to coordinate response from the control room or possibly from the designated emergency control center. But he was working with incomplete and rapidly changing information. He did not know how many people had been killed or injured in the initial explosion. He did not know the full extent of the fires or whether they could be controlled. He did not have clear visibility into whether the fire protection systems were functioning, and he was facing the most difficult decision any offshore installation manager could face: at what point does the situation become clearly unsurvivable, requiring immediate evacuation regardless of the risks involved? Workers throughout the platform were making their own assessments of the situation and their own decisions about what to do. In the accommodation module, approximately 100 off-duty workers had been awakened by the explosion and alarms. They emerged from their sleeping quarters to find smoke beginning to fill corridors, the platform continuing to shake from explosions and structural stresses, and emergency announcements telling them to proceed to muster stations. Muster stations were designated assembly points where workers would gather during emergencies so that personnel could be accounted for and so that evacuation could be organized if necessary. The muster stations on Piper Alpha were located on open deck areas near the lifeboats, the primary evacuation method for the platform. The idea was that workers would muster near the lifeboats so they would be in position to evacuate if the decision was made to abandon the platform. But as workers attempted to move from the accommodation module to the muster stations, they encountered terrifying conditions. Some routes were blocked by fire and smoke. Other routes exposed workers to intense heat radiating from the fires. The platform was continuing to shake from explosions as pressurized systems failed. Workers could see and hear the fires raging in the production areas. Some workers decided that attempting to reach muster stations through fire and smoke was more dangerous than remaining in the accommodation module. Others pushed through the smoke and heat to reach the assembly points, believing that following emergency procedures was their best chance of survival. Those who reached the muster stations found themselves in an increasingly untenable situation. The assembly points were on open deck areas with no protection from the heat, smoke and flames. As the fires intensified and spread, the muster stations became exposed to radiant heat that was painful even at distance. Smoke made breathing difficult. The platform was clearly not under control. Fires were growing rather than being suppressed. Explosions continued and no fireboats or external assistance had yet arrived. The lifeboats that were supposed to provide evacuation were proving difficult or impossible to use. Some boats had been damaged by the explosion or by falling debris. Others were positioned on the side of the platform that was now engulfed in fire, making them inaccessible. The lifeboat launching systems, davits and falls that lowered the boats to the water were complex mechanical systems that required careful operation and were vulnerable to damage from fire and explosions. Several of the boats could not be launched because their systems had failed or because workers could not safely reach them through the fire and smoke. The few lifeboats that workers did manage to launch faced additional deadly problems. The davit systems that lowered the boats to the water were designed to work smoothly under controlled conditions, but the violent shaking of the platform from continued explosions, the heat affecting metal components, and the terror and urgency of the situation meant that launches did not proceed as designed. Some boats descended unevenly as falls on one side released faster than the other, tilting the boats and throwing occupants against walls or out of the boats entirely. Other boats fell the last portion of the distance when davit systems failed completely, hitting the water with tremendous force that killed or seriously injured occupants, and sometimes breached the hulls. Even boats that reached the water intact faced challenges. The standard procedure was for lifeboats to move away from the platform under their own power once waterborne, but some boats' engines would not start, leaving them drifting near the burning platform. Others had crews who were injured or disoriented and could not operate the boats effectively. The cold North Sea water, the darkness, the smoke and flames from the platform, and the continuing explosions created a nightmarish environment for the few boats that did successfully evacuate personnel. As conditions on the platform deteriorated and as it became clear that lifeboats were not functioning as planned, individual workers faced an impossible choice. They could remain on the platform, either sheltering in the accommodation module or gathered at muster stations, hoping that the fires would be brought under control or that rescue would arrive. Or they could jump from the platform into the North Sea, a decision that seemed suicidal but which offered at least some chance of survival if rescue vessels could reach them quickly. Jumping from Piper Alpha meant falling approximately 175 feet, the equivalent of a 15-story building. At that height, hitting water is not fundamentally different from hitting concrete. The impact velocity after falling 175 feet is approximately 65 miles per hour. The human body striking water at that speed experiences forces that can cause fatal injuries, broken bones, internal trauma, concussions, spinal injuries. The impact can knock a person unconscious, ensuring that they drown even if the fall itself was not immediately fatal. Those who survived the impact faced immediate danger from the cold water. The North Sea in July has surface temperatures of approximately 10–12 degrees Celsius (54 Fahrenheit). Water this cold causes immediate physiological responses: gasping reflex, hyperventilation, rapid cooling of extremities, progressive loss of muscle control. Without protective equipment like survival suits, a person in 50-degree water faces unconsciousness from hypothermia within 30–60 minutes, and death within 2 to 3 hours. Most of the workers on Piper Alpha were wearing only the light clothing they had on when the explosion occurred, no flotation devices, no thermal protection, nothing to improve their chances of surviving in the water. But despite these terrible odds, jumping began to seem like the only option for workers who saw the fires intensifying, who felt the heat becoming unbearable, who witnessed continued explosions, and who realized that no effective firefighting was occurring, and no rescue was arriving. The first workers to jump made the decision in desperation, seeing no other option. Their jumps gave courage to others who followed, creating a cascading effect as more workers concluded that staying on the platform meant certain death while jumping offered at least a chance. Some workers helped each other prepare to jump. They gathered at edges of the platform away from the worst fires, helping colleagues over railings, offering encouragement, even holding hands before jumping together. These acts of solidarity and mutual support in the face of terror demonstrated the bonds that had formed among workers who lived and worked together in the isolated offshore environment. Some workers reported praying before jumping, others simply jumped without hesitation once they made the decision, not allowing themselves time to reconsider. The falls were terrifying. Several seconds of freefall in darkness, seeing the water rushing up, not knowing if they would survive the impact. Some workers instinctively tried to position themselves feet first and vertical, minimizing the surface area hitting water and protecting head and torso. Others simply fell however they happened to leave the platform. The impacts were brutal. Workers described feeling like they had been hit by a truck, having the wind knocked out of them, experiencing instant pain from the collision with water. Those who survived the impact and remained conscious faced the immediate challenge of staying afloat and staying alive. The cold water caused instant shock, gasping, disorientation, an overwhelming urge to climb out of the water even though there was nowhere to climb. Workers who were strong swimmers under normal conditions found their muscles not responding properly in the cold water. Those who had been injured in the fall, broken bones, concussions, internal injuries, faced additional challenges staying afloat and conscious. Some workers found debris to cling to, pieces of equipment that had fallen from the platform, life rings that had been thrown or fallen into the water, anything that would help them float and conserve energy. Others simply tried to swim away from the platform, knowing that getting distance from the fires and potential falling debris was important, but also knowing that swimming in their condition was nearly impossible. Most simply tried to stay afloat and stay conscious, waiting for rescue and hoping it would come before hypothermia or exhaustion made it impossible to continue. Meanwhile, approximately 20 minutes after the initial explosion, at around 10:20 p.m., a massive secondary explosion occurred that fundamentally changed the nature of the disaster. This explosion was far larger than the first, so powerful that it registered on seismographs on shore, and was visible as a massive fireball from the Scottish coast, 120 miles away. Witnesses on shore described seeing a brilliant flash of light on the horizon, followed by a huge column of flame rising into the night sky. The cause of this secondary explosion was the failure of one of the major pipelines connecting Piper Alpha to other platforms. The Tartan platform, located several miles from Piper Alpha, sent its oil production to Piper Alpha through a subsea pipeline for processing and export. The Claymore platform similarly sent natural gas to Piper Alpha through another pipeline. These interconnections were designed to maximize efficiency. Tartan and Claymore could produce oil and gas but had limited processing capability, so they sent their production to Piper Alpha, which had more extensive facilities. But this interconnection created a deadly vulnerability. When fires on Piper Alpha heated the incoming pipelines beyond their design limits, the steel pipes lost strength and eventually ruptured, and critically, both Tartan and Claymore continued pumping into their pipelines even after Piper Alpha was clearly on fire and experiencing explosions. The operators on these platforms initially did not know the severity of the situation on Piper Alpha. Their emergency procedures were ambiguous about when to shut down in response to problems on connected platforms, and there were economic and operational pressures not to shut down unnecessarily, as stopping production cost millions of dollars per day. When the Tartan oil pipeline ruptured due to fire damage, the result was catastrophic. The pipeline was carrying crude oil at high pressure and high flow rate, possibly several thousand barrels per minute. When the pipe failed, this enormous flow of oil was suddenly released directly into the fires on Piper Alpha. The oil sprayed out under pressure, atomizing into fine droplets that ignited instantly, creating a massive fireball. The release was continuous. Tartan was still pumping, meaning that thousands of barrels of crude oil per hour were being sprayed directly into the inferno, feeding fires that were already beyond control. When the Claymore gas pipeline ruptured shortly afterward, the effect was even more dramatic. Natural gas under pipeline pressure, hundreds of pounds per square inch, was released in enormous quantities directly into the fires. The gas ignited immediately, creating a blowtorch effect of incredible intensity. The flame from the ruptured gas line was visible for miles, a towering column of fire that turned night into day in the immediate area of the platform. These pipeline failures transformed what had been a serious fire into an absolutely catastrophic conflagration that made survival nearly impossible. The platform was now being fed with continuous supplies of fuel from external sources, creating fires of such intensity that steel structures were melting, concrete was spalling and cracking, and heat was radiating over enormous distances. Workers who had been sheltering in the accommodation module or at muster stations found themselves suddenly exposed to even more intense heat. The accommodation module itself, which had initially seemed like a safe refuge, began to heat up as fire surrounded it on multiple sides. The flare tower, which had been continuously burning excess gas under controlled conditions before the disaster, bent and collapsed from the extreme heat. Entire deck modules were consumed by flames. Equipment that was not directly burning was heated to temperatures that caused thermal failure, pipes rupturing from thermal expansion, vessels failing from overpressure, structural steel losing strength and deforming. The platform was literally melting and collapsing under the assault of fires fed by ruptured pipelines. Workers who had remained on the platform hoping for rescue or for fires to be controlled now faced a situation that was clearly unsurvivable. The accommodation module, where many had sheltered, was becoming an oven as heat penetrated through walls and through the ventilation system. Smoke was infiltrating every space. Carbon monoxide from the incomplete combustion of hydrocarbons, odorless and deadly, was likely causing many deaths as it displaced oxygen and poisoned those who inhaled it. Some workers who had initially chosen not to jump now made desperate last-moment attempts to escape. They moved through smoke-filled corridors, climbed over obstacles, reached edges of the platform, and jumped even though they were now weakened by smoke inhalation and even though they were jumping into an area surrounded by flames and filled with debris. Many of these late jumpers likely died either from the fall, from drowning immediately after impact, or from hypothermia within minutes of entering the water. The explosion and fires had triggered emergency responses from multiple directions. Other platforms in the area saw the flames and explosions from dozens of miles away. Shore-based facilities received emergency calls from Piper Alpha in the first minutes after the initial explosion, before communication systems were destroyed. The UK Coast Guard was alerted and began coordinating a massive search and rescue operation. Helicopters were launched from Aberdeen, taking off into the night on a flight of over 100 miles to reach the burning platform. Rescue vessels and supply boats that had been working in the area began heading at maximum speed toward Piper Alpha. But rescue faced enormous challenges. Helicopters approaching the platform found that the intense heat and smoke made it impossible to get close. The fires were radiating heat that could damage helicopter rotors and engines at distances that would be required for winch rescues. The smoke obscured visibility. Continued explosions on the platform sent debris flying upward, creating hazards that could destroy a helicopter. Several helicopter pilots attempted to approach closely enough to search for survivors on remaining sections of the platform or to potentially winch people off, but the conditions made it impossible. The best they could do was orbit at a distance, using searchlights to search the water for survivors, and radio their positions to surface vessels. Rescue vessels approaching by sea also faced significant dangers. The intense heat radiating from the platform could damage vessels that approached too closely. Falling debris, pieces of structure, equipment, pipe sections created hazards for vessels trying to get near enough to search for survivors. Oil slicks on the water surface, leaking from ruptured systems on the platform, created risks of fire spreading to the water. But several vessels managed to approach close enough to begin recovering survivors from the water, with crews using searchlights, life rings and rescue nets to pull exhausted and hypothermic workers from the sea. The recovery of survivors from the water was itself traumatic and dangerous. Workers who had been in the water for 30 minutes or more were severely hypothermic, many barely conscious, some going into cardiac arrest as they were pulled from the water and their bodies tried to rewarm. Rescue crews provided emergency treatment, warming blankets, hot drinks for those conscious enough to drink, CPR for those in cardiac arrest, treatment for injuries from the falls or from the explosion. The crews on rescue vessels became impromptu emergency rooms, treating multiple critically injured and hypothermic patients simultaneously while continuing to search for additional survivors. The rescue operation continued through the night. Helicopters and vessels searched the dark water using searchlights and night vision equipment, looking for survivors who might be clinging to debris or simply floating in survival suits or life jackets, though few workers had been able to access flotation devices before jumping. The search area was large because currents and winds had dispersed survivors over a wide area. The darkness, smoke and continued fires on the platform made the search extraordinarily difficult. As hours passed, the probability of finding additional living survivors decreased. Hypothermia in 50-degree water progresses relentlessly. Even strong, healthy individuals lose consciousness and die within 2 to 3 hours without thermal protection. By midnight, more than 2 hours after the initial explosion, anyone still in the water who had not been rescued was almost certainly dead from hypothermia. But the search continued because there was always a chance that someone had found particularly good flotation, or was unusually resistant to cold, or might still be rescued alive. By the morning of July 7, as dawn broke over the North Sea, the full horror of the disaster became visible. Piper Alpha was still burning, though the character of the fires had changed. The intense flames fed by ruptured pipelines continued, but much of the platform's structure had collapsed into the sea. The accommodation module, where many workers had sheltered hoping for rescue, was a burned-out shell. Deck structures had partially collapsed. The platform that had stood as a symbol of engineering achievement and offshore oil capability was now a twisted wreck of fire-damaged steel, barely recognizable as what it had been just 12 hours earlier. The rescue operation continued through the morning, now transitioning from searching for survivors to recovering bodies. But the intense fires and the structural collapse meant that most bodies could not be recovered. They had been consumed in the fires or were trapped in wreckage that could not be safely accessed. The final accounting was devastating: 167 men confirmed dead, making Piper Alpha the worst offshore oil disaster in history. Only 61 workers survived, most of them people who had jumped from the platform relatively early in the disaster and had been quickly recovered from the water by rescue vessels. The 167 dead represented workers from across the UK and several other countries. They ranged in age from 19 to late 50s. They included Occidental employees who had worked on Piper Alpha for years and contractors who had been on the platform for just days or weeks. Fathers and sons had worked together and died together. Friends who had gone offshore together for years did not come home. The disaster devastated the tight-knit North Sea oil community, where workers knew each other across different platforms and companies. For families, the hours and days following the disaster were agonizing. Initial reports indicated a major incident with casualties, but specific information about who had survived and who had died was slow to emerge. Families gathered at Aberdeen Airport and at Occidental's offices waiting for news. Lists of survivors were compiled slowly as rescued workers were identified and their families notified. But for many families, confirmation of death took days as it became clear that some workers were neither among the survivors nor among the bodies recovered. The bodies of most victims were never recovered. They were consumed in the fires that reached temperatures exceeding 1,000 degrees Celsius, or they were lost when portions of the platform collapsed into the sea, or they remained in wreckage that could not be safely accessed. For families, this added another layer of tragedy: no body to bury, no grave to visit, no physical closure to their loss. The dead were commemorated in memorial services, but many families struggled with the absence of remains and the knowledge that their loved one's final resting place was the wreckage of Piper Alpha. The immediate question facing investigators, government officials and the public was how this catastrophe had happened. Occidental moved quickly to express condolences and to state that they were cooperating fully with investigations. The UK government announced that a public inquiry would be held to investigate the disaster and make recommendations to prevent future tragedies. Lord Cullen, a respected Scottish judge, was appointed to lead the inquiry. Families of victims demanded answers about why their loved ones had died and who was responsible for the failures that caused the disaster. As investigators began examining the wreckage and interviewing survivors, a picture emerged of multiple failures, technical, procedural, and organizational, that had combined to create the catastrophe. The immediate cause was clear: a pressure safety valve had been removed from pump A for maintenance. The pump had then been started by night shift operators who were unaware it was not ready for service, and the resulting high-pressure leak of condensate had ignited and exploded. But this immediate cause raised profound questions about why the permit-to-work system had failed, why shift handover had not communicated the critical information about Pump A's status, and why the disaster had escalated so catastrophically once the initial explosion occurred. The investigation into the permit-to-work system revealed serious deficiencies. The permit that had been issued for maintenance on Pump A was found to be inadequately filled out, not clearly indicating that the pump should not be operated. The system for communicating permit information between shifts was inadequate. There was no rigorous checklist or sign-off procedure ensuring that incoming shift supervisors and operators knew about all ongoing maintenance work and equipment that was out of service. There was no physical lockout system, no tags on equipment, no disabled controls that would have prevented Pump A from being started even if operators were unaware of its status. Investigators also found that the hand-tightened blind flange was grossly inadequate for sealing a high-pressure opening. Proper procedure would have required the flange to be torqued to specific values using calibrated tools, ensuring a seal capable of withstanding full system pressure. The fact that the flange was only hand-tightened suggested either that workers did not understand the requirements or that they were taking shortcuts to save time. This finding raised questions about maintenance procedures, worker training, and supervision. The escalation of the disaster after the initial explosion revealed additional serious problems. The fire protection systems, which should have been able to contain and suppress fires, had not functioned adequately. The firewater pumps had not provided sufficient water supply to the deluge systems. Some pumps had not started when they should have. Others had been damaged quickly by the fires and explosions. The placement of pumps and their vulnerability to the very fires they were supposed to help control represented a design flaw. The platform's emergency response plans had been overwhelmed by the speed and intensity of the disaster. Key personnel were killed in the initial explosion, communication systems failed, and workers were left to make individual survival decisions without guidance. Most critically, the continued pumping of oil and gas from the connected Tartan and Claymore platforms turned a serious fire into an unsurvivable inferno. There were no automatic shutdown systems, and by the time the platforms shut down manually, enormous quantities of fuel had fed the fires. Lord Cullen's inquiry heard testimony from hundreds of witnesses and published a comprehensive 450-page report in 1990 that fundamentally changed offshore safety regulation. The report identified 106 recommendations and found that Occidental had failed to maintain adequate safety systems, that production pressures had overridden safety, and that regulatory oversight was insufficient. One of the most significant outcomes was the introduction of the safety case regime, requiring operators to conduct comprehensive risk assessments and demonstrate adequate controls. A new regulatory body, the Health and Safety Executive's Offshore Safety Division, was created with independence to enforce safety requirements. For Occidental, the consequences were severe: approximately $1 billion platform loss, millions in daily production revenue loss, and hundreds of millions in compensation payments. Criminal prosecutions were not pursued, which was controversial for many families who felt justice had not been served. The 167 victims' families formed support groups and advocacy organizations. Survivors faced severe burns, psychological trauma, PTSD, and survivor's guilt. The North Sea oil industry was forced to confront uncomfortable truths about prioritizing production over safety. Memorials were erected, including the Rose Garden Memorial in Aberdeen with 167 granite stones. The legacy of Piper Alpha became a worldwide case study demonstrating how multiple small failures can combine to create catastrophic accidents. Today, Piper Alpha remains the world's worst offshore oil disaster. The 167 workers who died paid the ultimate price for failures they did not create. Their deaths serve as permanent reminders that safety can never be compromised and that the pursuit of profit must never override the protection of human life.